Hey there, my name is Mike, and welcome to my channel. Today we are putting the final puzzle piece in our displacement, velocity, acceleration, kinematics picture. We talked about displacement in the last 3 videos. We talked about this idea that we could have an arrow that points from where we were to where we are, and we call that vector quantity displacement. We've talked about velocity, this idea that we take a displacement, the rate of change of displacement through time, delta x divided by delta t gives us some vector quantity v, velocity. And these two are analogs in the physical world to distance and speed. Of course, we want to be scientific, so we will use these. And today we are going to talk about acceleration, which is this idea of taking velocity now and taking the rate of change of it. So we take delta v divided by delta t, and it gives us this quantity a, acceleration. It is again a vector quantity. And to understand what it is, I'm going to start by showing you some lines. So here I have a graph set up, and this graph represents two things. It is velocity and it is time. So imagine, for instance, that we are looking at race cars. I'm an engineer, so I love cars, motorcycles, things that go burr and quick. So here I have on the time axis, just in elapsed time, think of like a stopwatch starting. And here I have a velocity curve. Velocity curves here. The y-axis represents the velocity. And let's say I'm just looking at the 0 to 60 times of various vehicles. So you might consider curve 1 here, where we have a lot of initial bursts of speed and acceleration. You can see if I move just a little bit on the time axis, look at how high I rise in the velocity axis. But as I go further, closer to 60 miles an hour, things start to slow down. Wind resistance starts to play into effect. The gears of my car being longer mean I have less torque that I'm able to spend and use to push the car forward. This is just what you experience in the real world. If you merge onto the highway, if from a dead standstill, the first 0 to 30 miles an hour, it doesn't matter what car you're in, it's fast. But then, 30 to 60, things start to slow down. And if you went further, 60 to 90, it's going to take forever. So this is a curve of what we might find in real life of the acceleration of like a typical car. Curve number 2 is something called a line of constant acceleration, and it represents, again, the same point. So it goes from 0 to 60 in the same time as line 1, this car here, but notice that it does so in a straight line. The acceleration, if I were to draw little arrows here, is constant across all of it. The velocity rises predictably. If we were to just look at velocity, all we would see is that we had at time 0 a velocity of 0, and at time, whatever this, call it t naught, t1, t final, we had a velocity of 60 miles an hour. And when we think that blandly about things, everything looks like curve 2. We need some extra value to distinguish between these types of curves. We need some sort of way to talk about the acceleration of an object. And we do that with acceleration. So I want to think about the slope of these graphs for a minute, and I've written some stuff here about the slope. Let's remember that the slope is the rise over run of an object, of a line. We call that the change in y divided by the change in x. So if I wanted to look at the slope, I would take a point here, I would take a point here, and I would see how much did y increase, and then how much did x increase. Then I would divide the increase in y by the increase or decrease in x. And that gives me my m, my slope. Now, if I wanted to find the slope at an instantaneous point, this is one of the first things they teach you in calculus. It would be good to know here, but if you don't worry. What we do is we take 2 points and we move them closer and closer and closer together until that arrow represents basically the slope instantaneous to this curve. We call that line the tangent line. Another way to think of it is the tangent line is the line that's parallel to a curve at a given point. So we actually use this a lot in engineering. If you're making like an engineering drawing of something, you'll use a tangent line on a circle to maybe represent like a surface that needs to be parallel at this point of like a cam lobe for an engine or something similar. Here's an example of something that I was working on in my engineering stuff, my engineering disciplines, and you might have a tangent line right here that's parallel to that circle. So this little crankcase detail comes out parallel at that curve to the circle. It is tangent to the circle. Hopefully that comes through. But basically it's just the instantaneous slope at this point. That is what the tangent line represents. Now do note, we're talking about the change in y divided by the change in x. Now we don't have an x and a y here because we've elected to draw a graph of t and v, time and velocity. The same rules apply, but we just have a difference of variables. So now, instead of delta y over delta x, we write delta v divided by delta t, right? And that slope, we know what this is. That's our newly discovered acceleration. So when we talk about the slope of velocity, we are looking at acceleration. In fact, we can run through this with a couple kind of rules to remember. And so I want you to drill this in your head. Make sure you understand this concept right here. Displacement exists. Velocity is the slope of displacement with respect to time. So if I have a graph of displacement and time, just like we had velocity and time, then the slope of that graph will give me the velocity. And finally, acceleration is the slope of velocity. So whenever I have velocity here and time here, any slope is acceleration. And let's go ahead and practice this. Let's do one with displacement, since I did say that's also the case. Here's a pretty simple graph showing time and then some x-axis right here, x of t, and it could be y of t or s of t. Remember, this is just a way to talk about displacement. And I'm going to draw a line that looks something like this. This would be a quadratic line, so we would write y equals x squared, and it is one curve that could represent displacement. And in fact, we will see this curve more when we talk about something called projectile motion. But what we are going to do then is look at the slope at a given point. And remember, we can take 2 points. This is a great time to show you how this works. And if I take 2 points and I connect them with an arrow here, look how close that slope gets to the curve. And if I were to make 1 point smaller and smaller and smaller, then this arrow would become closer and closer to where the actual, basically the slope at that point instantaneously. And for most of our purposes, what we can do to simplify this is just graphically think of like, okay, find the curve and then just draw a line parallel to it, tangent to it, and that's the slope. Now, what is our slope? M, in this case, is equal to the change in y divided by the change in x, which becomes the change in displacement divided by the change in time, which is velocity. That's right. So this guy continues to be true. Velocity is indeed the slope of displacement. Everything stems from displacement. Then it's all basically calculus. So that about covers what we need to know on this front. The last thing I want to say is just that we should also consider that we can convert one step backwards if need be. Now, there's a lot more calculus if we wanted to go from acceleration directly to displacement. But we can go from acceleration to velocity and velocity to displacement fairly simply, and we can do this just by writing out the equation. So think about this for a minute. Acceleration is equal to the change in velocity divided by the change in time, right? Well, if I multiply both sides by delta t, the change some interval of time, then what happens? I end up with a delta t is equal to the change in velocity. So if I moved, let's say, we're going to try and think of an example here that works. Here's a super simple one that works. If I am a box and something, say a gust of wind, is accelerating me at a constant 2 meters per second squared, if you're curious about the squared, I have a video on units in fundamentals. I believe it's 1.3. You can go check that out and understand why this is squared. But I'm being accelerated at 2 meters per second, or 2 meters per second squared. And what I want to know is, what is my velocity after 10 seconds go by? And what we can do is just multiply this time interval by this acceleration and find that my velocity after 10 seconds, v, is at least equal, at least changed by 10 times 2 equals 20 meters per second. And I say that it's changed by because let's say my initial velocity was 2. v0 equals, actually let's say it's 1 meter per second. Then I would have no way of knowing that initial 1 meter per second difference here. Now, there are ways to solve for it, right? If I knew information about like where I ended up, I might be able to figure out that I had a starting velocity, but there's no way to take acceleration. If I just multiply this, 2 times 10, a times the time interval, delta t, then I'm going to get the change in velocity. This acceleration has increased my velocity by 20 meters per second. I don't know what I was starting at, but at least I know what the acceleration did. So just know that you can interconvert. Likewise, if I had a displacement times a change, or no, I'm sorry. Let's say I had displacement divided by time, like we normally do, is equal to v. Then I can figure out displacement by multiplying the velocity times some interval of time, and that's equal to displacement. So these do work like regular quantities. Just because you have a delta there, don't let it freak you out. These are still regular quantities. So if I'm given a displacement and a velocity and I don't know time, I can solve for it by figuring these things out and just doing the algebra. And we'll do some algebra later in this chapter. So if this is kind of iffy right now, don't worry. We're going to go through this and explain, and you're going to have a great grasp on it, I promise. But I think that covers it for this video. Stay tuned for the next one. We are going to do some worked examples. And I think with this unit, now that we're actually synthesizing the information, putting it all together, it would be good to do. So do check those. I'll kind of make them like homework problems, and I might leave like a problem in the description below or like a challenge problem. So we'll make it fun, but I will see you guys in the next one. Thanks for tuning in, and thank you for 1,000 subs, by the way. That's freaking cool, dude. All right, I'll see you guys in the next one. Peace.